So this is the second half of our lecture on buffers as part of our series on Chapter 16 of ionic equilibria. So in the last video we finished off with looking at solving this problem where we're looking at the pH of a buffer that has acetic acid in it, sodium acetate, and sodium hydroxide added to it. So we want to compare the effect of pH of adding 0.01 moles of sodium hydroxide to a buffer that has 0.1 moles of acetic acid and 0.1 moles of sodium acetate in 1 liter of water, and by comparing that to a non-buffer system where 0.01 moles of sodium hydroxide is added to 1 liter of pure water. So here we've given the pKa of the acetic acid, which is 4.745. And if we set up our Henderson-Hasselbalch equation, so pH equals the pKa plus the log of the base over the acid, I substitute in my pKa value and my initial concentration of my weak base, and that weak base concentration comes from my sodium acetate ion plus the 0.01 moles that was created when the sodium hydroxide neutralized the acetic acid, and the 0.09 moles of the HA is from the initial amount of acetic acid, so the 0.1 minus 0.01 moles of sodium hydroxide that was used to neutralize that 0.01 moles of acetic acid to give a total of 0.09 moles of acetic acid. So if you'll remember, we did some of these calculations in a previous slide, so that's why we're kind of going through this more quickly. But the pH of that buffer system is 4.83. Now if we compare that to a non-buffer system, remember with this system the sodium hydroxide is a strong base, so it completely dissociates. So this is a one-way reaction. So the hydroxide concentration is going to be equal to the concentration of the sodium hydroxide because it completely dissociates. So 0.01 moles of sodium hydroxide was added to 1 liter of pure water, so the molarity is 0.01 divided by 1, which gives us 0.01. Then I can find the pOH by taking the negative log of the hydroxide concentration, which is that 0.01 that we found earlier. So if we take the negative log of that number, we get a value of 2. Now to compare these numbers, I need to have them both in the same unit, so we need both of pH. So if I take the pH plus the pOH, it gives me 14. So 14 minus the pOH gives me a pH of 12. So adding 0.01 moles of sodium hydroxide to water increased the pH of the water from 7 to 12. So you have a large increase by adding that amount of sodium hydroxide, whereas adding it to the buffer changed the pH of the buffer very little. Now we can also create basic buffers, and basic buffers work very similarly to the acid buffers. So here we have a base in solution and its conjugate acid, so the protonated form of the base. So buffers can also be made by mixing a weak base with a soluble salt of its conjugate acid, so it would be the protonated form of the base. In this example here of a basic buffer, we are combining the weak base ammonia with its conjugate acid, the protonated form of ammonia, which is ammonium, and the ammonium is supplied as part of the ammonium chloride. And again, remember the chloride is a neutral anion, but the ammonium ion is acidic cation. So when we add the conjugate acid and the weak base, we get a buffer system that has a basic pH. So in this problem here, we're asked to find the pH of a buffer that is 0.5 molar ammonia, and they give us the pKa of the ammonia, and in that buffer there's also 0.2 molar ammonium chloride. So to start this problem, I've written out the chemical equation. So ammonia plus water will form an equilibrium to make ammonium hydroxide. And since they've given me the pKb, I'm going to solve for the pKa, and the pKa plus the pKb equals 14. So 14 minus the pKb equals 9.25. I can then plug this into the Henderson-Hasselbalch equation so that the pH equals the pKa plus the log of the base over the acid. I substitute in my 9.25, which is my pKa, and the log of the base concentration. So the concentration of my base is 0.5 molar over my acid concentration. My acid concentration is 0.2 molar of ammonium. So if I stick this into my calculator, I should get a pH of 9.65. And with many of my equations, I need to check to see if the approximation that I've used is okay. So I'm finding my hydronium ion concentration. I take 10, raise it to the negative pH, and my hydronium concentration is 2.23 times 10 to the minus 10th. So the hydronium concentration over the initial acid concentration times 100. This gives me a value much less than 5, so I'm okay with this approximation. Now I'm going to work the same problem as the previous slide, but I'm just going to work it in a slightly different way because we are working with a base. And if you'll notice in the previous slide, I worked it like we were working with an acid, so I used the pH and I used the pKa. But there's also a basic form of the Henderson-Hasselbalch equation. And that basic form of the Henderson-Hasselbalch equation is the POH equals the pKb plus the log of the acid over the base. So remember where the Henderson-Hasselbalch for the acid form, so pH equals the pKa plus the log of the base over the acid. This time we have POH instead of pH, pKb instead of pKa, and here we have acid over base instead of base over the acid. So I plug in my pKb value, that 4.75, and the log of my acid over my base, so 0.2 over 0.5, and I get a pH value of 4.35. Again, I can solve for my hydroxide concentration just to check to make sure that my approximation is valid. So the hydroxide concentration over the initial base concentration times 100 gives us a value much less than 5, so I'm okay with the approximation that's built into the Henderson-Hasselbalch equation. But I also have to remember I'm not quite done because in the problem they asked for the pH of the buffer, and so far I found the POH. So if I take my POH and subtract that from my 14, so 14 minus the POH equals the pH, and I get a value of 9.65. So notice I got the exact same value as I did on the previous slide, working with the acid form of the Henderson-Hasselbalch equation. So both methods are valid, you just have to choose which one you prefer. Okay, same problem again, a third way. Because sometimes people don't know when to use the Henderson-Hasselbalch equation, I'm just showing you that you can solve this problem without setting up the Henderson-Hasselbalch equation. So again, I start off with my chemical reaction, so the NH3 combining with water to make the ammonium hydroxide. And my initial concentrations are 0.50 molar ammonia, 0.20 molar ammonium, and we're going to assume that the hydroxide concentration initially is 0. And our change, we do minus x since this is an equilibrium, and it's a 1-to-1 mole ratio, so plus x of the ammonium and plus x of the hydroxide concentration. And my ending value is 0.50 minus x for the ammonia and 0.20 molar plus x for the ammonium and x for the hydroxide concentration. To finish solving this, I need to set up my mass action equation. So this is a base, so I need my Kb equals my products over my reactants. So the 0.2 plus x times x over 0.50 minus x. Well, I don't have my Kb, but they did give me my pKb. And I know that 10 raised to the negative 4.75, so 10 raised to the negative pKb equals my Kb. So I can plug this value in to my equation for my mass action. And I'm going to make the assumption that X is fairly small, so it's not going to have a big change in my ammonium or my ammonium concentration. So I'm going to just remove those to simplify my math. Then I'm going to multiply both sides of the equation by 0.5, divides both sides by 0.2. And when I put that in my calculator, I get an X value of 4.4457 times 10 to the negative fifth. So if I take the negative log of X, and remember X is my hydroxide concentration, that will give me my POH. And in my calculator, I get 4.35. But they don't want the POH, they want the pH. So 14 minus the POH gives me my pH, and that pH value is 9.65. So notice I've solved the same problem 3 different times, one using the acid form of the Henderson-Hasselbalch equation, once using the base form of the Henderson-Hasselbalch equation, and once using the method where we're deriving everything out. And remember, the only time that we can use the Henderson-Hasselbalch is when we know that we have a buffer. And this problem was nice because they told us we had a buffer situation. Now let's talk about buffering effectiveness. A good buffer should be able to neutralize moderate amounts of added acid or base. However, there's a limit to how much can be added before the pH changes significantly. And the buffering capacity is the amount of acid or base a buffer can neutralize. And the buffering range is the pH range at which the buffer can actually be effective. So the buffering capacity is how much it can take in without having a big change in the pH, and the buffering range is the pH range that the buffer is actually effective over. And the effectiveness of a buffer depends on 2 factors. The first one is the relative amounts of acid and base, and the second is the absolute concentrations of acid and base. So we're going to look at the first situation, the effective relative amounts of acid and conjugate base. Here we have 2 buffer systems. Buffer 1 has 0.1 moles of weak acid and 0.1 moles of the conjugate base, whereas buffer 2 has a larger concentration of the weak acid, so it has 0.18 moles, and a lower concentration of the 0.02 moles of the A minus, that conjugate base. And they give us the initial pH values. And for this HA acid, so this generic acid, we're going to be using a pKa of 5. And remember, the Henderson-Hasselbalch equation relates the pH and the pKa plus the log of the base over the acid. So we're going to add 0.01 moles of sodium hydroxide to both buffers, and we're going to look to see how that changes the pH. So in buffer 1, we have the same number of moles of weak acid and conjugate base, and we're adding 0.01 moles of sodium hydroxide. So after the sodium hydroxide has been added, because remember the sodium hydroxide, that hydroxide will combine with the weak acid and it will neutralize the weak acid to make the conjugate base. So this is a one-way reaction when you have a neutralization reaction. And then the increased concentration of the A minus will affect the equilibrium. So we've added 0.01 moles of sodium hydroxide. One equivalent of sodium hydroxide will neutralize the same number of equivalents of HA, so we've lost 0.01 equivalents of HA, so we have a total of 0.09 moles of HA. But this will make 0.01 moles of the A minus, so our total concentration now of the A minus is 0.110, so our concentration of our A minus has gone up. And in the case of buffer 2, we see the similar changes where the HA concentration has gone down by 0.01 and the A minus concentration has gone up by 0.01 due to the neutralization of the hydroxide reacting with the HA. So I then calculate my pH using the Henderson-Hasselbalch. So pH equals a pKa plus a log of the base over the acid, so the 0.11 divided by the 0.09. That gives me a value of 5.09. and the percent change in the pH is 1.8%. But in buffer 2, if we calculate the new pH, so 5 plus the log of the base over the acid, 0.03 over 0.17 equals 4.25. So the change in this system is even greater. So a buffer is most effective with equal concentrations of acid and base. So in buffer 1, where the concentration of the weak acid and the conjugate base were the same initially, we had a very small change in the pH when the sodium hydroxide was added. Whereas with buffer system 2, we had a larger amount of the weak acid compared to the conjugate base, so when the sodium hydroxide was added, we had a larger change in the pH compared to buffer 1. A buffer is most effective with equal concentrations of acid and base. So in the previous slide, we were comparing the effects of relative concentrations of the acid and base. Now we want to look at the effect of absolute concentrations of acid and conjugate base. So in buffer system 1, we have 0.5 moles of the weak acid and 0.5 moles of the weak base. And in buffer system 2, we have 0.05 moles of HA and 0.05 moles of the conjugate base. So we have a tenth of the acid in the base in buffer system 2 than we do in buffer system 1. So again, we're going to add 0.01 moles of sodium hydroxide to both buffers and see how that affects the pH. Well, when I do my limiting reagent problem and I consume part of my HA with my sodium hydroxide in that neutralization reaction, my HA concentration goes down, my A- concentration goes up, and if I plug this into my Henderson-Hasselbalch equation, I get a pH of 5.02. And this is a percent change of 0.4%. Now in buffer system 2, when I add the sodium hydroxide, again I neutralize part of the weak acid. That weak acid that's consumed, that 0.01 moles of HA that's consumed, gets converted to A-, and this is why the A- concentration increases to 0.06. And my pH that I calculated using the Henderson-Hasselbalch equation is 5.18. And when I calculate the percent change in this buffer system, the percent change is 3.6%. So notice that the more concentrated buffer system 1, had a smaller change in the pH than did the more dilute buffer, which had a change of 3.6% in the pH. So a buffer is most effective when the concentrations of acid and base are largest. So in summary, the effectiveness of buffers. A buffer will be most effective when the acid to base ratio equals 1, so you have equal concentrations of acid and base. It's also effective when the base to acid ratio falls between 0.1 and 10. We said it's most effective at 1, but it's still effective if that ratio ranges between 0.1 and 10. And a buffer will be most effective when the acid and the base concentrations are large. We have said that a buffer will be effective when the acid to base ratio falls between 10 and 0.1. If we substitute into the Henderson-Hasselbalch equation, we can calculate the maximum and minimum pH at which the buffer will be effective. So here is my Henderson-Hasselbalch equation. I'm going to put in the lowest pH, so when I have a higher concentration of the hydronium ion. So this would correspond to the 0.1 base to acid ratio. When I plug this into my Henderson-Hasselbalch equation, the log of 0.10 is -1, so pH equals a pKa minus 1. And at the highest pH, when that ratio is 10, the log of 10 is 1, so the pH equals pKa plus 1. Therefore, the effective pH range of a buffer is the pKa value plus or minus 1 unit. So when you're choosing an acid to make a buffer, choose an acid whose pKa is closest to the pH of the buffer that you want to make. Here in this example, they're asking us which of the following acids would be the best choice to combine with its sodium salt to make a buffer with pH 4.25. So remember, I'm looking for an acid whose value, the peak plus or minus 1 unit of the pKa value, will include this pH. So chlorous acid has a pKa of 1.95, so the highest pH this would be effective in is 2.95. So I can exclude the chlorous acid. Nitrous acid, the highest pH value would be 4.34. So this falls within my pH range. But there's also formic acid, and its pH would be effective to a pH range up to 4.74. And then the hypochlorous acid, the lowest pH at which it would be effective would be 6.54. So this is 4.25 does not fall within this, so I can exclude the hypochlorous acid. And the formic acid has a pKa value closest to that of the pH of the desired buffer system that we'd like to create. So formic acid would be our best choice. So the pKa of formic acid is closest to the desired pH of the buffer, so it would give the most effective buffering range. In our next example problem, they're asking us what ratio of sodium formate to formic acid would be required to make this buffer with a pH of 4.25. So remember from the previous slide that the formic acid pKa is 3.74, and I'm setting up my Henderson-Hasselbalch equation. I can plug in my pKa value, so that's what I've done there, and they want a pH value of 4.25, so I'm going to calculate the ratio of my base to my acid that would give me that pH. So 4.25 minus 3.74 gives me a value of 0.51. And to get rid of the log, I raise both of these sides to the power of 10, or 10 raised to these powers, so 10 raised to the 0.51 and 10 raised to the log of the base of the acid concentration. So with my rules of logs, the 10 and the log would disappear, and so the base to acid concentration ratio would be equal to 3.24. So to make the buffer with a pH of 4.25, you would use 3.24 times as much sodium formate as you would formic acid. The buffering capacity is the amount of acid or base that can be added to a buffer without destroying its effectiveness. And the buffering capacity increases with increasing absolute concentration of the buffer components. As the base to acid ratio approaches 1, the ability of the buffer to neutralize both added acid and base improves. Buffers that need to work mainly with added acid typically have base concentrations higher than that of the acid. And buffers that need to work mainly with added base generally have acid concentrations greater than the base, because when you're adding the base, there needs to be more acid to neutralize that base to maintain the pH more effectively. This is the end of our second video dealing with buffers. In the next set of videos for Chapter 16, we will be looking at titration curves and titrations dealing with strong acid, strong base systems, and weak acid, strong base, and weak base, strong acids.